building an efficient code by unsupervised learning. Now let's outline a couple of learning rules to develop the neural transform for the efficient codes. And such learning rules should also be the basis for adaptation of the efficient codes when visual input environment changes. First, let's consider a simple case. There's only one output neuron O, and we have inputs coming from n input nodes. And with these weights K1, K2, etc., we have the output O as a linear sum of the inputs with these weights. So now the question is, how can a biological system learn such weights starting from some arbitrary initial value K's? And this is such a proposed rule that shows how should weight K change. And this is the derivative of K with t times t, and this is the learning rate, epsilon. So if epsilon is small, then the weight changes only slowly. Let's look at an example when I is equal to 1. So this is then K1. According to this rule, its change is determined by the value of O, S1, and K1. So it's O, S1, and K1. All of these values are directly linked to K1 available to the synapse locally. So therefore, this weight change can happen just by the information locally available to this K1. And this change is not dependent on some other instruction or remote information coming here to tell K1 how to change. That means such a learning rule is very easy to implement in a neural circuit. So it's biologically plausible, and this is applicable to all of these cases. This first term in the learning rule means that the weight K should increase when its presynaptic neuron S and its postsynaptic neuron O are both firing. And so when they are both firing, the weight should increase. And this kind of learning rule is called Hebbian learning rule. Now let's look in detail. In the first term of this right-hand side of the equation, let's write this O out as this weighted sum. Since we already have this index I, let's use index J for this weighted sum. So we have this. Now, if we assume that this K changes slowly, so that from one input vector to another input vector, this K changes very little. So now let's average this over many input vectors S. Okay, so we get that. And so therefore, this becomes the average over this multiplication over the input ensemble. So that's the correlation. And similarly, this is the ensemble average of O squared. So cleaning up, we write the results here, and we notice that this correlation is an element, ij's element, in the input correlation matrix RS. Now let's multiply both sides of this equation by 2ki, and then we sum over I. We get this result. On the left-hand side, this derivative times 2ki is the derivative of ki squared, and then we sum over I. On the right-hand side, this first term, so sum over j becomes sum over I and j, and times ki, yeah? And the factor of 2, we already take it out. And similarly for the second term, ki times ki is ki squared, and again, sum over I, and again, a factor of 2 is out. We notice that this term is equal to O squared over ensemble average, just by noticing that O was here, and so therefore O squared will be something looking like that, then do ensemble average, it's like that, yeah? And so therefore this O squared is same as that O squared, so the whole thing is equal to this, with the O squared factored out. Now, once the learning has finished, 8k will no longer change, so all these derivatives will be equal to 0, so is this equal to 0? So when the left hand equal to 0, this means then after learning, this summation of ki squared will converge to value 1. And so this is converged to a normalization of the vector k for this neuron. Now let's look deeper. When the learning converges, this left-hand side is also 0 because k no longer changes. Then this right-hand side can be written as this equation. Yeah, this means after learning, this k vector is an eigenvector of this correlation matrix. Okay, and with this as the eigenvalue. You can work it out that this term is the same as doing a derivative of this whole thing in a bracket, half of it, yeah, just by doing this derivative, and you will get this result. Now, notice that this is actually this first term in the learning rule, and since it is part of doing this derivative, that means this learning rule is trying to do a gradient descent of the negative this term. Therefore, it is trying to minimize the negative this, and so therefore this, the negative this, is like it's trying to minimize this objective function. Yeah, and since this is equal to O squared, that means it is trying to maximize O squared average with the constraint by the second term to normalize the weight vector. And so therefore, after the learning, not only is this weight vector going to be an eigenvector, it is actually the principal eigenvector because the eigenvalue O squared ensemble average is going to be maximized. So therefore, it's the eigenvector with the maximum eigenvalue, the principal eigenvector. We can even include noise so that Si is now corrupted by noise, and O is therefore this one, yeah. And the noise in different nodes are assumed to be independent of each other and identically distributed Gaussian noise. We can then repeat the whole learning process and still get the same result. And because this result maximizes O squared, this means the learning will maximize this mutual information between the output O and the input S. So the learning achieves maximum information with the constraint that the weight vector is normalized. When we have multiple output nodes, O1, O2, etc., we have another learning rule. Let this be the neural network dynamics. We have output nodes O, input nodes S, and the I's output node OI is driven by the corresponding input, but is also inhibited by other output nodes OJ with this weights Wij. So this is a weight matrix, and so therefore this is a recurrent interaction matrix between the output nodes. This network may look unfamiliar if you are only used to feed-forward network rather than this recurrent network. However, once this recurrent network has converged its dynamics, this O no longer changes, so the left-hand side is equal to 0. The right-hand side should also be equal to 0. Therefore, we have this as the outcome. So O equal to W inverse S. So therefore, this recurrent network is equivalent to a feed-forward network after its convergence, with this as the feed-forward weights. Let's have this learning rule. So for the weight to change, it changes for each weight Wij changes according to this formula. So this Wij connects Oj with Oi. It changes first of all depending on this Si, which is direct input to Oi, and depend on the presynaptic activity Oj. And the change also depends on the weight itself. So all of these are local, yeah. So therefore, this learning rule only depends on local activities, with these quantities really in the neighborhood of Wij, the changing weight itself, yeah. And look at these two equations. There are two different dynamics. One is the dynamic of the neural activity when the weight is not changing. The other is the changing weight. And we again want to have a situation where the weight change is much slower than the neural activity change. And this can be achieved by taking tau tilde much larger than tau, because tau tilde is the time constant for the change of W, while tau is the time constant, the time scale for the change of O. This means when the learning converges, we have this result. Now, if we plug in what S is into that, we will reach this result. So SO now becomes this, and therefore this comes over. This is the equation that can only be achieved if OK, OJ, the correlation, is 0 between different K and J's. So this learning rule achieves decorrelation among the output units. This is the most efficient code when the input noise is 0. So in fact, not only is this output units decorrelated from each other, each output unit also comes to a fixed variance. So the activity doesn't really blow up to infinity, but fixed to a finite quantity by this learning rule. Let's say that suddenly the input environment changes. So the input statistics changes so that this output decorrelation no longer holds. Consequently, going backwards, that means this equation no longer holds. That means this is no longer 0 on average. Then this weight will change again. This is the adaptation of weights by the changes of input statistics until the weight learns to a new value to make this decorrelation hold again in a new environment, resulting in the new set of weights.